welcome back. So until now, we've only talked about the motion of objects. That's a category in physics called kinematics. But now we're going to start with a different section called dynamics. So dynamics tries to explain why things move or why things stop moving. And for that, we need to introduce the concept of a force. So if you have a ball that is still and you want it to start moving, you have to exert a force on it. You have to make a force on it. If you have a ball that is moving and you want to stop it, you also need to exert a force on it. So changing a motion requires an acceleration. If it's going at a certain speed and you want it to stop, you have to decelerate it. If it's still or going at a speed and you want to accelerate it, you need an acceleration. So we can actually define force as something that tries to cause an acceleration. Okay, but why do I say tries to cause an acceleration and not causes an acceleration? That's because if I try to push a wall or push an elephant, I will be making a force, but the object won't move. It won't accelerate, even though there is a force. So I push the wall with all my force, even though it's not accelerating, there is a force there. So anything that tries to cause an acceleration of an object is called a force. So we have two examples of this. First, if an object is staying still, it'll stay there for eternity unless a force comes and disturbs it and makes it change its state of motion. If an object is moving at a constant speed and no force acts on it, it will continue moving at that constant speed in a straight line forever. So here you may think, wait, that's not true. I mean, if I make a ball roll through the ground, at some point it's going to stop. But the point there is that there is a force acting on it. There's friction. The ground exerts friction, which is going to stop the ball. You can think of a situation where there are no forces, and that is in space. If there is an asteroid moving through space, if it doesn't collide with anything, it'll continue moving in a straight line forever. So this brings us to Newton's first law of motion. Newton has 3 laws of motion, and we're going to look at each of them one by one. So Newton's first law says the following. An object in motion will stay in motion, and an object at rest will stay at rest unless acted upon by an unbalanced force. So what this means is that if an object is moving at a constant speed, not accelerating, or if an object is at rest, there has to be no unbalanced forces acting on it. So if there are forces, they have to cancel each other out. So here the important thing that we need to figure out is if there is something called a net force. A net force. And a net force means the vector sum of all the forces acting on an object. So if we have, for example, a box, and I push the box from the left with a certain force, and someone else pushes the box from the right with the same force, then our forces will cancel out, and there's no way we're going to move or accelerate this box. So that would be balanced forces. Unbalanced forces would be if someone else was pushing here and it's with a much bigger force. So this is unbalanced because the forces pushing to the left are bigger than the forces pushing to the right. So we have to take into account the directions. We also need to take into account forces pushing down and forces pushing up. If they all cancel each other out, the object only has balanced forces acting on it. If they don't, it has unbalanced forces. So let's do an example to show this in a better way. So in this example, I drew 3 boxes, identical boxes. Let's say each of them has a mass of 2 kilograms, and they all have a total force acting on them of 10 newtons. So 5 and 5, 7 and 3, and 1 and 9. 10 newtons is the total force, but not the net force. For the net force, we have to take into account the direction. So in the first box, there's 5 to the right and 5 to the left, and they cancel each other out. So the net force is 5 minus 5, which is 0. We're going to use the letter N for the unit, but I'll get to that in a second. In the second example, the net force would be 7 minus 3. So we get a net force of 4 to the right, because the bigger force is to the right. And here we have 1 minus 9, which is negative 8. So because the direction of the bigger force is to the left, the direction of the net force is also to the left. So we have 8 to the left, or -8. So because there is no net force here, no unbalanced forces, box A will not accelerate. It will stay at rest if it was at rest before. Box B will accelerate to the right because it has an unbalanced force of 4 to the right, and box C will accelerate to the left because it has an unbalanced force of 8 to the left. And finally, this first law of motion is also called the law of inertia. So let's write that word down. Inertia is the reluctance of an object to change its state of motion. So an object may be at rest and it doesn't want to stop being at rest, or an object is moving at a constant velocity and it doesn't want to stop moving or move at a faster velocity. And inertia is actually proportional to mass. So inertia is proportional to mass. So we can think of this the following way. Imagine if there was a truck moving at a constant speed, a very big truck, and you wanted to stop it. You put your hand on it, but you're not going to be able to stop it. It's very reluctant to stop moving. It has a very big inertia. But if there's a toy car coming towards you at the same speed, you can probably stop it with your finger. So that means the inertia of the toy car is a lot less than the inertia of the truck, because the truck has a lot more mass than the toy car. Now let's move on to Newton's second law of motion. Newton's second law of motion states that the force F required to give an acceleration A to an object of mass m is given by the equation F equals m times A. That is a very important equation that you're going to be using for the rest of physics. So what does this mean? This means that the acceleration that an object receives is directly proportional to the force. That means if you push harder, you're going to accelerate the object more. And it's inversely proportional to the mass. Because if you solve for acceleration in this equation, acceleration is force over mass. You would have to take mass below to divide. So it's inversely proportional to mass. That means that the heavier an object is, the more massive it is, the bigger it is, the harder it is to put to motion or stop it from moving. So for example, if you wanted to give the same acceleration to a refrigerator and to a bottle of water, you would have to require a much bigger force to push the refrigerator and set it in motion than to the bottle of water. Now let's look at the units of force. So force is a mass times an acceleration, and we know that the units of mass are kilograms, and the units of acceleration are meters per second squared. So the units for force, which we write like this, are equal to kilograms times, because it's mass times acceleration, so kilograms times meters per second squared. So that is actually the whole unit of force. Kilograms times meters per second squared. But because force is used so much in physics, they give this unit a new name called newtons. And the letter is N. So when I tell you I apply a force of 1 Newton, what I'm saying is just that the force is equal to 1 kilogram times meters per second squared. It's the same thing, just a new name for the unit of force. So let's try to use this equation to figure out the acceleration of each of the blocks. And remember, we don't care about what number was on the right and what number was on the left. We only care about the net force, So in this case, let's use this equation, A equals F over m. The 3 boxes have a mass of 2 kilograms, so we're going to put 2 on the bottom. So in this case, the acceleration is equal to the net force 0 over 2. And 0 over 2 is just 0. In this case, we have 4. So the acceleration is going to be 4 newtons over 2 kilograms, which is 2 meters per second squared. Right? So because the net force was bigger, there was an acceleration. And then here, in this one, we have an acceleration of, the force is 8, but negative because it's to the left. So we have negative 8 over 2 will give us an acceleration of negative 4 meters per second squared. And remember, the negative just means to the left. So the acceleration of box C will be 4 meters per second squared to the left. So remember, the only thing we care about is the net force. So the acceleration will be the same if we're pushing a box with a giant force of 100 newtons, or 100 people are pushing the box with a really tiny force of 1 newton. We only care about the net force. Now let's do one more example and move on to Newton's third law. So we have another example here. There's a box with a mass of 20 kilograms, and one man is pushing it to the right with a force of 15 newtons, and another one is pushing it to the left with a force of 5 newtons. What will be the acceleration of the box? So the first thing we have to figure out is the net force. So again, for the net force, we subtract forces to the right, which are 15 newtons, minus forces to the left, which are 5 newtons, and we get a resultant force of 15 minus 5, 10 newtons. Once we have our force, we can use the equation for acceleration, which is force over mass. The net force is 10 newtons, and the mass is 20 kilograms. So what we're going to get here is 10 over 20, which is 0.5, and newtons over kilograms will give us the unit of acceleration, which is meters per second squared. So the acceleration of the box will be 0.5 meters per second squared. Finally, let's move on to Newton's third law of motion. So Newton's third law of motion states that to every action there is an equal and opposite reaction. And here, the words action and reaction are talking about forces. So what does this mean? An action is a force that I make. For example, I punch the wall. And the reaction means that the wall punches my hand back. So, for example, if I make a force of 20 newtons towards the wall will make a force towards my hand of 20 newtons as well. And that's why it hurts when I punch my hand into the wall. So these two forces are always equal in magnitude. So the magnitude is always, if I punch with 20 newtons, it will answer back with 20 newtons. But the direction is opposite. So what that means is that if I push towards the wall, the force that I will feel is away from the wall. If I push, for example, an elephant and it's really hard, the elephant is pushing back on me in the opposite direction, so I will feel a recoil force. Or if a gun shoots a bullet, the gun will push the bullet forward and the bullet will push the gun backwards. That's why you feel a recoil when you shoot a gun. But the acceleration of the bullet and the acceleration of the gun are not the same, because even though the force on both is the same, it's an equal reaction. The mass of the bullet is a lot smaller than the mass of the gun. So because of Newton's second law that we just saw, the bullet will accelerate much faster than the gun. So let's do an example of this. So imagine we have an elephant and it's running through the field and it crashes against a butterfly and continues running. So what happens in that reaction? The force is 1 Newton. So the elephant hits the butterfly with a force of 1 Newton. That means the butterfly also hits the elephant with a force of 1 Newton. But the butterfly has a mass of 0.005 kilograms and the elephant has a mass of 1,000 kilograms. So let's look at the acceleration of each of these. So the acceleration of the butterfly will be force over mass. The force is 1 Newton and the mass is 0.005 kilograms. So that will give us an acceleration of 200 meters per second squared. The elephant also has a force of 1 Newton, but it has a mass of 1,000 kilograms. So its acceleration will be 0.001 meters per second squared. So in real life, what does that look like? It looks like the elephant basically doesn't have to stop at all because of the butterfly. It doesn't realize what's going on, while the butterfly will fly backwards at 200 meters per second squared. So for the butterfly, this reaction was a very traumatic experience, while the elephant didn't even notice. So a very important thing to keep in mind when you're doing these types of exercises, even though there are two forces of 1 Newton, they act on different objects. So one of them acts on the butterfly, the other one acts on the elephant. So you can never add these two forces. You can't add them because they don't both act on the same object. So keep that in mind. Now let's look very quickly at the difference between weight and mass. This is one of the biggest misconceptions that students have in physics, and it's very important that it's clear. So, do you guys remember the acceleration due to gravity? We had an acceleration that was equal to negative g, which is negative 9.8 meters per second squared. And we just learned this class that for every acceleration, there has to be a force behind it that is causing it. So in this case, that force is what we call the force of gravity, because we're talking about the acceleration due to gravity. So the force of gravity, we can actually calculate it with our equation. So we know that force is equal to mass times acceleration. So it's going to be equal to mass times, in this case, negative g, or mass times negative 9.8 meters per second squared. So this is actually the definition of the force of gravity. It's always multiplying the mass in kilograms by negative 9.8 meters per second squared. Now, this force of gravity receives another name, and that is weight. So even though we use the word weight very commonly in our lives, what it really means is we're talking about a force, a specific force that gravity makes and that is pushing us down towards the earth. So weight is actually given in the units of newtons. So for example, if there is a man and he has a mass of 80 kilograms, a regular man, his weight is going to depend on where he is. If he's on Earth, the acceleration due to gravity is negative 9.8. So the weight of the man, which we can call W or we can call Fg for F, force of gravity, is going to be equal to his mass times negative g, or negative m times g. So his weight on Earth is equal to 80 times negative 9.8, which is equal to negative 784 newtons. So remember, unit of weight is newtons. So these are two different things. Mass talks about the amount of matter that makes up the man, how much muscle he has, how much water, how much fat, and the weight talks about how much Earth's gravity is pulling him in. So he has a mass of 80 and a weight of negative 784 newtons on Earth. But what if this guy is on the moon? So on the moon, the acceleration due to gravity on the moon is equal to negative 1.6 meters per second squared. So if we were asking about the weight of the man on the moon, we would have to multiply his mass of 80 times the negative 1.6, and we would get 128 newtons. So always remember that the weight depends on the location. The moon, Jupiter, Earth, Saturn, while the mass will always stay the same. He will always have a mass of 80 kilograms unless he goes on a diet or does exercise. So you can practice with some examples of passing weight to mass and mass to weight using this equation here, or in summary, F equals negative m times g. This is the equation for the force due to gravity.